A very good day to everyone. In this video, we are going to discuss about Lecture 4, Energy Balance for Open System. Our group member consists of Hani Haziqah binti Arjunaidi, Aizatul Nabila binti Abdul Khalik, Raihan Nur Hanani binti Muhammad Safingi, Sharifah Ummul Aminah binti Syed Jamil. In this video, we are going to discuss about open system, mass balance for a steady flow process, energy analysis of steady flow system, mass and energy balance for a steady flow process, application in steady flow engineering devices such as nozzles and diffuser, turbines and compressor, throttling valve, mixing chamber, heat exchanger, pipe and duct flow.
So what is open system? An open system is a system which can exchange both energy and matter with its surroundings. It is also known as control volume. So, to take this example here, energy can enter the system through work done on the piston, work done by the piston, or by heat being transferred into the system, or by heat being transferred out of the system. As for the mass flow for the system, a mass can enter the system and can exit the system. To obtain the mass and energy balance, we first have to apply the conservation of mass principle. This principle enables us to write a mass balance in terms of the system that we have defined. The rate of change of mass contained within the control volume, dmCV over dt, is equal to the sum of mass flows entering the control volume minus the sum of mass flows exiting the control volume. For steady operation, the mass of fluid within the control volume does not change with time, so the derivative is zero. The results of the mass balance is that the mass flow into the system at station 1 must be equal to the mass flow out of the system at station 2. Thus, M1 is equal to M2. So let's continue by evaluating the mass flow rate at each station. Mass flow is equal to rho VA. We can write this for both station 1 and station 2. Thus, rho 1 V1 A1 is equal to rho 2 V2 A2. Now, the fluid element has got flow energy, internal energy, kinetic energy, and potential energy, which is theta equal to PV plus U plus V squared over 2 plus GZ. The flow energy and internal energy is taken out automatically by enthalpy, H equal to U plus PV. Now, the fluid element becomes like this. Theta equal to H plus V squared over 2 plus GZ. Note that the rate of energy transport, E mass, is equal to m dot theta is equal to m dot H plus V squared over 2 plus GZ. So, we must account them for energy associated with the flowing fluid. So, E is equal to E in plus EKE plus EPE plus H, which also can be said as E equal to E in plus mv squared over 2 plus mgz plus mh. Now, if we have a steady state condition, then there is no change in the energy of system with time. So then, E in is equal to E out under steady state condition. So, we can write a total energy balance by noting that E in is equal to E out for an open system, so we have Q in plus W in plus the sum of M H plus V squared over 2 plus GZ equal to Q out plus W out plus M H plus V squared over 2 plus GZ. In this example, we will apply the conservation of mass principle to diffuser operating at steady state. A diffuser is a device that reduces flow velocity by changing area. An incompressible fluid with a density of 1000 kilo per meter cube enters a diffuser at a velocity of 10 meter per second through an area of 0.1 meter squared. At the exit, the density is equal to the inlet density. The exit area is 10 times the inlet area. Find the exit flow velocity. So, let's start by defining our system. We start with the schematic of the diffuser of flow path with an increasing area. The inlet is labeled as station 1 and the outlet is labeled as station 2. Next, we define our system boundary as the velocity enclosed by the wall of the diffuser. We apply the conservation equation to this control volume. Mass crosses the system boundary at two locations, S1 and S2. The next step in solving the open system is to apply the conservation of mass principle. This principle enables us to write a mass balance in terms of the system that we have defined. The rate of change of mass contained within the control volume is equal to the sum of mass flows entering the control volume minus the sum of mass flows exiting the control volume. For steady operation, the time derivative is 0. So M1 is equal to M2. We evaluate the mass flow rate, which is M1 is equal to ρ1 V1 A1, as for M2 is equal to ρ2 V2 A2. Thus, we have ρ1 V1 A1 equal to ρ2 V2 A2. We can solve this equation for the velocity at station 2, which is what we are looking for in this problem. The velocity at station 2 is equal to the ρ at 1 divided by ρ at 2 times A1 divided by A2 times V1. By substituting the values, we get V2 equal to 1 meter per second.
Now we are going to discuss about the application in steady flow engineering devices. We are going to discuss about 6 types of devices. The first one, nozzles and diffuser. Second one, turbines and compressor. Third one, throttling valve. Fourth one, mixing chambers. The fifth, heat exchanger. And the last one is pipe and duct flow.